Hi pre-calculus friends, here we are in section 6.3. We're going to be talking about graphing sine and cosine functions. Our vocabulary has two phrases in it, periodic and period. And so let's start with the idea of a periodic. A periodic function is one that has a repeating, kind of predictable situation like the one that I'm showing you here. So a periodic function is one that kind of cycles through. It has a cycle. It has a beginning and an end, and then it begins again in terms of its motion. Okay, so periodic means periodically it repeats, and it does that infinitely, forever and ever. And so that is a periodic function, and the period of a function can best be described as one full cycle. So what I'll do, the way I created the periodic function above was taking a bunch of these things and redrawing them over and over again. And so basically this would be one period. And so one period is the time it takes for the one cycle to go through to go through one cycle. So if, for instance, I'm looking on this graph and I am saying that from the beginning of the cycle to the end is like, let's say this was 4 and this was 8, I would say, oh, a whole cycle would take 4 whatever units of x I'm dealing with. So 4 minutes, seconds, whatever, for a period of 4 after we go through 4 different values on the x-axis. All right, so that's periodic and that's period. Let's go ahead and look at a more mathematical way of determining it. So a periodic function and the period of the function is given in the following way. A function is periodic if for some value alpha, f of x is equal to f of x plus alpha for each x in the domain. So if you want to think about that, if we started off here and let's say alpha was this length here, then that would define it as periodic, because we know for every alpha we're going to get to the next value. Does that make sense? Hopefully it does. You can read it over and kind of make sure it's on point with what you understand. Okay, so for each x in the domain, then the least positive value of alpha is going to be the period. And if you notice, my length of alpha was equivalent to this like 4 length that we talked about from here to here, because if I were to do it, I would have done something like that. That would have been alpha, and therefore that would have been 4. So the period is going to be the time it takes for that to repeat. All right, with that in mind, let's go ahead and check out this first example. Determine if each function is periodic. If so, state the period. And so if we look at this function, we can see that it's periodic because we see that it has kind of a portion that kind of repeats, right? If we wanted to take this part here, we could say, oh, it repeats over and over again. We can see it happening, and it happens in a way that it is exactly the same distance from the other ones, right? And because of that, we can also determine the period. And the period in this case is going to be 4, because after 4 units on the x-axis, no matter where we start, we could start here and end up here, add 4 units up, 2 plus 4 is 6, and we're right at the beginning. We could start at 7 and add 4 to that, and we get to 11, and we can see we end up exactly where we started. So this is definitely a period, and the period is 4. Let's go ahead and do that. Each interval is 4 units. The value of the function repeats each interval for 4 units, and the function is periodic, and therefore it's 4. If we look at this one, part B of number 1, we notice that it kind of seems predictable which periodic functions are, but it is not periodic, because if you notice, we don't have that situation where there's a specific place where we keep getting the same value over and over again if we just go further enough on the x-axis. In fact, this seems to be going up. So this is not periodic. This is not a periodic function, and therefore we don't have to find the period. If we look at this chart, just reminding us a little bit about the idea. The reason why we're talking about periodic functions is because the sine and the cosine function are periodic. And what we're going to do here is just kind of remind ourselves of what some of the values of sine are for different values of x. And so if x is negative 2 pi, then we see that the sine is 0, and we have these values that repeat. You can see 0, square root of 2 over 2, 1, square root of 2 over 2, and that should give you some indication of the periodicity of the function, of the sine function. So what we're going to do is graph the sine function. It might be easier for me to pull up a graph on Desmos. Let's do that. Okay, so if you take a look at what we have here, I just pulled this up from Desmos. I didn't draw it in, as you can tell, but just for the sake of neatness, we can see negative 2 pi is going to give us 0. Negative 7 pi over 4 is going to give us this number, which is close to like 0.87, I believe. And then when we get to negative 3 pi over 2, we're here at 1, and then we're coming down to that same 0.8 value, and then we're coming all the way back down to 0. And so I'm just like literally looking at this and seeing that we have this periodic function. And notice, a couple things that you want to notice is that the sine function starts at 0. Unlike the cosine function, which we'll talk about, the maximum value that we have here, let's see if I can write on this, the maximum value that we have here is 1, whereas the minimum value is negative 1. So we have a range of negative 1 to positive 1. And this kind of summarizes a lot of the information that we have about the sine function. So the period is 2 pi. The domain is the set of all real numbers. So domain, remember, are the x values. We can do this forever, guys. We can keep going. Doesn't matter. We can find the sine of all those angles. No matter how high you go or low. The range is the set of real numbers between negative 1 and 1 inclusive. The x-intercepts are located at pi times n, where n is an integer. Let's look at our graph and consider what that is. Oh, look at that. Every time we get to a multiple of pi, we are at 0, right? We are at 0. So that this is specific qualities of the sine function. They won't be exactly the same for the cosine function. The y-intercept is 0. We discussed that. The maximum values y equals 1 appears at certain places. So that's going to be at pi over 2. Any integer multiple of 2 pi plus pi over 2 is where you're going to get your max, and any integer multiple of 2 pi plus 3 pi over 2 is where you'll get your minimum. And so you can look at this at your leisure when you get a chance, guys. Okay, so let's look at this next one. Find sine of 9 pi over 2 by referring to the graph of the sine function. So I'm just going to roll up to the sine function and see if we can consider that. 9 pi over 2 is going to be not on this graph. So how can we consider that? Okay, so for number 2, we're going to find the sine of 9 pi over 2 by referring to the graph of the sine function. And we could see that 9 pi over 2 is going to be 4.5 pi over 2, if you think of it that way. So this is, or 4.5 pi, not pi over 2. So we have pi, 2 pi, 3 pi, 4 pi, 4.5 pi is right here. And so that should indicate what our value is. So since this is 9 pi over 2, or 4.5 pi, we can see that the value of that is 1. So the sine of that 9 pi over 2 equals 1. Again, I'm going to use the graph of the sine function in order to answer this question. It says, find the values, plural, of theta for which sine of theta is equal to 0. And so, let's see. We already kind of know this because we just talked about the intercept values. But if you notice here where y is equal to 0, I'm drawing this horizontal line over here. Maybe I should draw it in a highlighted line. There we go. So what we're concerned about here is all the places that intersect the graph such that it intersects this, hopefully, the x-axis or the y equals 0 line. And those would be these places here. So how can we describe that? How can we describe all of these values? So the value is, what we would say is that theta, this is true for all theta equaling n pi, where n is an element of the integers. Okay, so as long as n is an integer and we multiply it by pi, we're going to get a place where theta, that's going to be a theta value that will equal 0. In example 4, we're asked to determine, graph the sine function between 3 pi and 5 pi. And so what we want to do is, I personally would always think about what the actual sine function looks like. We have a couple cool things that we know about the sine function, which is that it intersects at every whole number multiple of pi. And so this would be pi. It intersects the x-axis at every whole number multiple of pi. So then this is what our x-axis can look like, 4 pi and then 5 pi. And I know that it's going to go up, down, come up again, up, right, up, down, come up, down, and then so I'm going down and up and down again. And so that is going to be the answer that we are looking for here. So let me make it look a little bit bolder. So we have that to look for. There we go. And there's our answer. Number 5 is really neat because it's going to show an application of the sine function and well, I'm going to call them sinusoidal functions because this could just as easily be a cosine function, as we'll see later on. But what you'll notice is that a lot of things that are cyclical, whether in terms of time, will often be sinusoidal in nature. And so what they're showing here is the sine is the value. They're not showing the sine of anything. They're showing the values of the temperature over a 24-month period in Asheville and in Baltimore. Okay, and so if you notice, it looks a lot like a sine curve, which is pretty cool. And so we're going to basically analyze that. They gave us the equations for them, which right now may not make as much sense, but later on it will make a whole lot of sense. And it'll give you a lot in terms of just what's going on. You will be able to build these equations as well. But they're showing the temperature values in relationship to the month, and we are asked to answer 2 questions. What is the average temperature for each city for month 13? And so we just go to month 13, which is here, and we can see that the average temperature for Baltimore is about 32 degrees, and the average temperature for Asheville looks to be about 37. Now write that down. So Baltimore, let's go ahead and get a pen. Baltimore will be approximately 32 degrees and Asheville will be approximately 37 degrees. And which city has the greatest fluctuation in temperature? And so we're talking about the highest and the lowest point, the greatest, and that's going to be Baltimore. And you can see that from the graph, right? Okay. So now we're looking at a table of values for the cosine, and this is going to bring us to the cosine function. I want you to pay attention to how different and how similar the cosine curve is to the sine curve. So right here in red, you can see that we have the cosine function, which is going to match up with these values here. So I'm going to write here y equals the cosine of x That's the graph here. And what I did is I left the sine function in the back so you can see it and kind of get a sense of how they compare. So instead of starting at the lowest point, cosine starts, if I'm considering the y-axis or the value at 0 to be the beginning, the cosine value starts at 1 and then it goes down and it comes up. And we'll see all the same things in terms of this continuation, the period being 2 pi, just as the period for the sine curve is 2 pi. And we'll see similarities in that way, except what we'll notice is that the 0 values, where the cosine is 0, does not happen at the multiples of pi. It happens at basically the odd multiples of pi over 2. If you can kind of walk with me on that. This is pi over 2. And this is 2 pi over 2, but this would be 3 pi over 2, and then we can continue on in either direction. So this is what your cosine curve looks like, very, very similar to your sine curve. And this chart gives us some good information as to where the maximum values hit, where the minimum values are, where the zeros are, and the range, which is the same as the other function we dealt with, the sine function, and so forth and so on. Let's go ahead and look at this value here. It says determine whether the graph represents a sine or a y equals sine or y equals cosine function. And so for me, I think the key that's important is where are the zeros? Where is this function hitting the x-axis? And this function seems to be hitting the x-axis, not at multiples of pi, but at odd multiples of pi over 2. So this would be negative 17 pi over 2, and this would be negative 15 pi over 2. And so this seems to be working with the concepts we saw with cosine of x. So this is going to be the cosine of x function. And actually that's it. I thought we had a little bit more, but that's all we got. Let me know if you need any more assistance with this, guys. Let me know if there's something that I can clarify, and I look forward to talking to you all soon. Bye-bye.